Hi everyone, my name is André and this is joint work with Alberto Lerner and Philippe Cudre-Mauroux from the University of Fribourg and Alex Forencich from UC San Diego. In this talk, we will show that current RDMA networking cards are not adequate for database systems in terms of performance with current and future networking speeds. We will propose an extension to RDMA which is more expressive with an extensible set of primitives, and we will show an architecture for a next generation networking card. RDMA stands for Remote Direct Memory Access, which gives the NIC direct access to the host's memory. The CPU is only involved by sending data descriptions to the NIC. The data fetching and sending part has no CPU involvement. This leads to great performance. But this changes once we deal with small data pieces. Now suddenly, all kinds of overheads kill the performance. Unfortunately, data-intensive applications deal often with small values, such as integers. Database systems work around this by gathering all those small pieces and copying them into one big contiguous area. And with that, we get once again high throughput, but at the cost of CPU cycles. However, in database systems, the data is generally not scattered around randomly, but close together and highly structured. RDMA is not able to exploit those two properties, proximity and regularity, giving us the same throughput as in the previous picture. With D-RDMA, we hope to change that. In this talk, I will quickly illustrate the problem a bit more in detail. Then we will look at the abstraction that we expose to the application. And finally, we take a quick tour of how D-RDMA NIC might look like. Let's say we have a distributed column store with 3 servers, each executing a query plan that contains exchange operators. On server 1, there's a table with 3 columns, which is shuffled between the 3 servers. So row 1 goes to the red server, row 2 to blue server, row 3 doesn't need to be transmitted since it already is on server 1. The next row is red again, and so on. If we wanted to implement this with RDMA, we would have to fill a control structure for every single value. For instance, for the 2 red rows, you would need to fill out 2 work requests, 6 SGE, SGE being our RDMA control structure that is essentially a pointer and a length. We took a PCIe logic analyzer to observe the communication between the CPU and the NIC. And it turns out that we not only need to describe every single value, but the NIC also issues a separate PCIe read for every single one. And in this case, we actually end up sending more control data to the NIC than the NIC will fetch in payload data. So we might as well have just sent the data directly. What database systems do instead is copy out. They copy the data to a transmission buffer that can then efficiently be handled with RDMA. However, this costs both valuable CPU cycles and memory bandwidth. Both this and previous solution yield very poor results. Copy out wastes a full CPU core to get to 18 gigabits per second, meaning we would need 5 CPU cores to reach line speed. The previous zero copy approach is even worse, using half a core to send control structures to the NIC and reaching an admissible 1.2 gigabits per second. One problem with RDMA here is that we have to send so much control data. The second problem are the small DMA reads. To quantify the problem, we ran a micro benchmark on the NIC that does sequential reads of a given size. As you can see in the graph, to near line speed, the reads need to be at least 256 bytes. Below that, we can often nearly double the throughput by doubling the read size. Actually, at the lower end it is even worse, because the reads not only fetch less data, but they also take longer. So hopefully now I convinced you that we need to reduce the amount of control structures to describe the data and that we should be doing bigger DMA reads. So how do we need to modify RDMA to make this happen? RDMA has certain constraints that we want to get rid of. If RDMA data has to be described in the same order as it appears in the packets. Instead, we want to declare where the data is using a more compact description in the form of patterns. The NIC must fetch the data in the same way it is described in the control structures. Instead, the card should determine the DMA by its own. It should not just issue one DMA per SG, but rather combine them in a way it sees fit, which allows it to take advantage of adjacency. And finally, the NIC should be allowed to transfer data, even if that data doesn't end up being needed. And we call this D-RDMA for declarative RDMA. D-RDMA is essentially two extensions to RDMA, a more expressive abstraction to describe the data that we call non-contiguous region, and a shared send queue, which allows us to optimize across connections. Overall, the process is very similar. We initialize the connections, send control data to the NIC, but now the NIC uses an optimizer to determine the DMA schedule, which then executes and finally puts the exact same packets on the wires as RDMA would. Non-contiguous regions are similar to work requests in that the sense that you use them to inform the NIC about what data to fetch. But they are more compact in their description and can describe many packets at once. The only real requirement we have is that the optimizer needs to be able to reason about where the data and the gaps are. The most basic non-contiguous region we can think of is a strided region, which basically declares a memory region as an array of elements of a certain size. We have a base pointer to the start of the array and how big an element in the array is. The number of elements determines the overall size. In the array, there are gaps. In other words, elements that will not end up on the wire, like the local data in the shuffle. And then there is a period after which the pattern of data and gaps repeats. We can also spell it out as one gap at every 2 starting at 1. Or on the right side, with a period of 3, one gap every 3 starting at 2. Coming back to our previous example, to implement it, we need 3 strided regions for the red server, since the 3 columns are in separate memory regions. And then the same thing for the blue one. We then send all of them to a shared queue, such that the optimizer will be able to merge the red and blue strided regions. This way we can assemble packets that contain data from different parts of the memory and also might have very different structures. Let's also quickly look at how we could build a NIC supporting D-RDMA. If we blow up the NIC from our previous discussion, you will find many of the same components as a traditional NIC, such as the DMA engine and the packetizer. But also some new components, most prominently the optimizer, which we'll have a closer look in a second. We also have a highly segmented memory and the assembler. The assembler gets the location and description of the data from the optimizer and is notified by the DMA engine once it has been fetched from memory. It assembles the payload and hands it off to the packetizer. The optimizer gets the non-contiguous regions from the driver. For instance, this region with 2 gaps. It then enumerates the different possibilities to fetch all that data and picks the best one. For instance, here it would consider 3 DMA reads, 2 DMA reads where 1 gap is followed, or just fetching the whole thing. In this case, it would determine that it should fetch all the data. So we're still experimenting with what kind of non-contiguous regions we should go for. One possibility we are considering is a bitmap region, where a bitmap determines whether a given element in an array should be transmitted or not. Another option is the pointer mapped region, which is similar to an SGE, but instead of just a length, we can declare a pattern that only fetches part of the data where the pointer points to. There are still a lot of open research questions on the optimizer. Should we always get the optimal DMA schedule with dynamic programming, or is there a simple approximate solution that is good enough and could be implemented in hardware? And there lay some challenges ahead of how to do memory management on the card. To conclude, the current approach of copy-out is not viable with today's and especially future networking speeds. We should replace the imperative interface of RDMA with a declarative one and give the card more control over how it fetches data. With that, we can free CPU and memory bandwidth that the database can use. A full NIC implementation is ongoing. Thank you.